Alright, y'all. So today we're going to get started on doing some more Pythagorean theorem stuff and special right triangles. So, Pythagorean theorem. Yesterday we proved to ourselves that the Pythagorean theorem is a squared plus b squared equals c squared. We had a and b as the legs of that triangle, which means that they make the right angle on that triangle. And we had C, which was the hypotenuse, and that is the side always across from the right angle. So let's say we have a right triangle with side lengths of 3, 4, and x. And I say, I want you to figure out what x is. First off, we know that the side lengths of 3 and 4 are the legs, because they are the sides that produce that right angle. And we know that the long side across from that right angle is the hypotenuse. So the formula a squared plus b squared equals c squared, we know that a and b are the legs, and c is the hypotenuse. So we can plug in 4 and 3 for a and b in that formula. And we're going to set it equal to x squared. And so now from here, once we've got it plugged in, all we really need to do is evaluate 4 squared and 3 squared. 4 squared is 16, 3 squared is 9, and we set that equal to x squared. And so 16 plus 9, we can simplify that further into 25. So we have 25 equals x squared. And so to solve for x, all I really need to do is take the square root of both sides. When I do that, I get the square root of 25 equal to 5, and x is equal to 5. And so this is a special type of right triangle. These three numbers, 3, 4, and 5, are called a Pythagorean triple because all three of those sides of that right triangle are whole numbers. But that's definitely not the case for everything. So what we're going to do is look at another one that doesn't necessarily have a pretty hypotenuse side. So how about this one? We have a right triangle with side lengths of 2 and 6. So when you start plugging in those values, you get 2 squared plus 6 squared equals x squared, which simplifies down to 4 plus 36 equals x squared. 4 plus 36 adds to 40, and so we have 40 equals x squared. And so my next step is to take the square root of both sides. But when I do that, problem is I get this really ugly number. It's like 6 point something something something, very ugly. I don't want that number. And so instead, whenever I take this square root of both sides, we're just going to simplify the radical expression square root of 40, like we did in our radical expressions unit. So we do that fancy division where we put 40 in a box, start with the lowest prime number. Does 2 go into 40? Yes, it does. 2 goes into 40 20 times. But 20 is not a prime number. So we put a box around 20 and say that 2 goes into 20 10 times. 10 is still not a prime number either, though. And so we put 10 in that box, and we say that 2 goes into 10 5 times. And now we're done because 5 is a prime number. We have broken 40 down into its prime factors. So to get our answer, what we've got to do is group numbers that come in pairs of 2. So I have one pair of 2's. For my simplified answer, that pair of 2's is going to go on the outside of my radical expression. Then whatever is left over, the 2 and the 5 on the bottom, I'm just going to multiply them back together. 2 times 5 is 10, and so I put a 10 on the inside of my radical. So the simplified answer is just 2 root 10. So whenever you can, I need you to be able to simplify a radical expression like this rather than that really ugly decimal number of 2.6 something. So why don't you try your hand at these next couple of problems. I've got 3 Pythagorean theorem problems. These first 2 I've given you both the legs, and I want you to solve for the hypotenuse. This last one, though, don't get tripped up on it. I've given you a hypotenuse, and I've given you a leg. This is the hypotenuse, this is the leg. And I need you to find the other leg. So you're going to have to do 9 squared plus something squared equals 15 squared. Okay, so don't let that trip you up. So take a couple minutes, work on this, and I'll let you check your answers in just a moment. Alright, y'all. Go ahead and wrap up what you're working on. If you all need another second to work on this, go ahead and pause the video now. But if you're ready, go ahead and look up here. Hopefully you got the answers of 10, 2 root 26, and 12 as your missing side lengths. If you didn't, double check your work and see if there was a mistake. If that doesn't help you, just ask me on Monday. I'll be glad to work it out with you. So, let's move on to our special right triangles. So yesterday we talked about one of them. We talked about the 30, 60, 90 right triangle. And the cool thing about these type of triangles is if you know one side length, you automatically know all 3. So, the side opposite the 30-degree angle, we're just going to call it x. So, the rule is whatever that side of x is, the hypotenuse is double that length. So that's why I have 2x there. 2 times x is double the length. And then the side across from the 60-degree angle, that's our weird side. We always are going to have a square root of 3 in front of it, and it's x times the square root of 3. And so that's what we did yesterday whenever we took that equilateral triangle and cut it in half and did the Pythagorean theorem to find this missing side length, the x root 3 side length. So for example, consider this 30, 60, 90 right triangle. Given that the side length opposite the 30-degree angle is 4, we can just go ahead and bust out those other 2 side lengths really, really easily. So, if the side opposite 30 is 4, the side opposite the right angle is twice the length of 4, which is 8. And so then we can go from there and say, okay, well, that weird side, the 60-degree, the side opposite the 60-degree angle, is just going to be this 4 times root 3. And if I had given you another type of problem like this, let's say I gave you this one, where I went ahead and just gave you the ugly side of 5 root 3. You would know that the short side, the one across from the 30-degree angle, is just the 5 right here. And you would know that the hypotenuse, the side across from the 90-degree angle, is just twice this number. So 2 times 5 is 10. So really the only thing you need to know about these triangles is the pattern they follow. Both of these, the 30, 60, 90 that we learned yesterday, and the one we're going to learn about next, they're just patterns. So, try these. Sketch these three triangles and fill in the missing sides. Now don't let this middle one fool you up. It's still a 30, 60, 90, 30, 60, 90. The only thing I did was just knock it over. So, don't panic. It's still a 30, 60, 90. You just have to get used to the rules that the side opposite the 60-degree angle has that root of 3 in it. So take a few minutes. I'm going to show you the answers in just a second. Alright, y'all, if you need just another minute, go ahead and pause the video. Otherwise, what is going to happen is I'm going to show you the answers. So hopefully you got these missing links. If you did not, go ahead, double check your work. If that still doesn't work for you, just ask me on Monday. Okay? So, the next type of triangle that we're going to be working on is called a 45-45-90 triangle. And it has kind of the same little pattern stuff going on. Okay? So, yesterday we derived the pattern of a 30-60-90 triangle by cutting a equilateral triangle in half. What we're going to do today is derive the pattern from a square. And any old square is going to work, right? It doesn't matter. And so this side length could be 8, this side length could be 10, this side length could be 36 million. We don't know, so what we're going to do is just call it x. All of these side lengths are x, because it's a square. All side lengths are congruent. And so if it's a square also, we know that all of the angle measures are right angles, meaning they're 90 degrees. And so how we get this 45-45-90 triangle is we're going to cut this square from one corner to the other, from corner to corner. The line we're about to draw is called a diagonal. And so this is going to cut the square into two congruent triangles. We're only going to want to worry about one for right now. Okay? And so there was a right angle here, and there was a right angle here, but we cut them in half with that diagonal. And so if this was 90 and we cut 90 in half, what's left over is 45-degree angles. So what's cool is we already know two of these side lengths. And if we do the Pythagorean theorem, we can set up that third side really, really easily. So the two lengths of our legs are x, so we know that x squared plus x squared should equal c squared, this hypotenuse squared. And so let's clean this up a little bit. If I have something plus itself, that's really just two of those somethings added together. And so x squared plus x squared is just 2x squared. So 2x squared equals c squared. And so now my inclination is to just take the square root of both sides, right? So when we take the square root of 2x squared, we're going to get a really ugly number because the square root of 2 is not a nice clean number. And so we're just going to leave it in radical form. But I can take the square root of x squared. The square root of x squared cancels the square root and squared out. And all that's left over is the x. So I bring this x out front of the radical and get x root 2. Right? I took the square root of x squared, didn't take the square root of 2. They're still together. And so this is just a simplified version of the square root of 2x squared. And so this is still equal to the square root of c squared. And when I take the square root of c squared, I just get C. So 45, 45, 90 triangles are super, super easy because really they're just two numbers that you need to know. The legs are both the same number, and the hypotenuse is just that number times the square root of 2. So I have x, x, x root 2. So let's try a couple examples. This triangle, it's got a leg length of 3. And so if this is a 45, 45, 90 triangle like we said it is, then this isn't the only leg that's going to be a length of 3. So is this leg down here. In that third side, the hypotenuse, if we did all of this Pythagorean theorem stuff out here, we would get that 18 equals c squared. And if I simplify the square root of 18, I just get 3 root 2. So that number out here comes right here, times the square root of 2. So I hope that seems easy, because it is. It's very easy. It is certifiably easy. Like, it's just easy, okay? So, what you're going to do, try a couple examples. All of these missing side lengths, I want you to sketch these triangles, try to fill them in. Alright, y'all. So, hopefully because this is certifiably easy, you already have all of these side lengths filled in. If you do not, go ahead and pause this video so that you can give yourself an extra bit of time. But the answers are this. So, again, all of the legs are the same number. All of the hypotenusi are just that number times the square root of 2. So if you didn't get those answers, hopefully you did. Double check your work to see if there was a mistake. And if that doesn't work, check with me on Monday. Okay, so up next, what's going to happen is we're going to take our break. Once we take our break and come back in, we're going to do one of those walkabouts. The walkabout is on the green sheets of paper around the room. That's why the word walkabout's in green. We're going to do the green sheets of paper around the room. There are 10 of those sheets of paper. Each of them have a letter on them, just like they always do. You start at any letter in the room, work on the problem that's on that letter, and then your answer should be at the top of another sheet of paper somewhere else in the room. You're going to have a little bit of time to work on that, and after that, we're going to do your quiz. So instead of a Friday quiz, we're having a Thursday quiz, because we don't have school tomorrow. So, your quiz is going to be on some blue sheets of paper. But first, take your break. Once you're done with your break, you're going to come back in, do your walkabout. Once everybody's done with the walkabout, we're going to do our quiz. Okay? Alright, y'all. Let's take a break.